Hello, welcome to the functional evolution of object-oriented programming. I'm James Ward, a developer advocate on Google Cloud.
Hi, I'm Josh Suereth. I'm a staff engineer at Google Cloud.
Let's talk about the cycle of learnings. So when we are using some paradigm, let's say object-oriented programming or whatever programming paradigm you want to pick, oftentimes we'll find some limitations in that paradigm. For example, I used to work with Java EE and found some limitations with doing things in the Java EE EJB way. Josh, what's the limitation that you found with Java EE?
Well, it was actually quite hard to test. The objects were pretty heavyweight and had a lot of stuff associated with them. So it was really hard to get a good isolated test on anything.
So then what we did to deal with those kinds of limitations was to develop some patterns. And for example, in this space, we started using XML dependency injection and just POJOs instead of the things like EJBs where we had to extend interfaces and that sort of thing. And so that was great that we had some patterns to help us deal with this. But what is happening in programming, what continues to happen, is that when we develop these patterns, oftentimes these patterns will percolate into the underlying programming languages and frameworks. So for example, with following on with XML dependency injection in that pattern was we developed a new pattern for doing this with annotations. And so that allowed us to evolve our programming language and our frameworks to deal with some of those original limitations. So let's dive into some of these ideas a little bit further. Let's start first with an example where I'm going to call a function. And Josh, we're going to play a little game. So I've got a function here called AddOne, and you'll see I pass a integer here of 2 and get an integer back. So let's run this thing and let's see what happens here when I run this. And I'm going to have you guess what actually happens. Okay, I've got a function. It takes a parameter of 2. What do you think the output's going to be here? What do you think
it should be 2 plus 1, which is 3.
Let's try it. 3. You are correct. Okay, now if we call that same function, same inputs, again, what do you think is going to happen this time?
Well, I mean, it should be the same thing.
Wrong. It is 4. And what about now? What if I call it a third time? What do you think it's going to be?
I mean, it should be 3, but in this case, I'm going to guess it's 4.
Wrong. It is not even an integer. It is null.
Oh, man.
Okay. And now, one last chance. What do you think it's going to be this time?
It's going to be null plus 1, which I think is 1.
Actually, it is an illegal state exception.
Oh, man.
Which is not even a value. Not even a return value on that one. Okay. So let's go look at AddOne to see what was actually happening. We have a function that's taking an integer, but you'll see I've got this global mutable state here, which this function is mutating. And so that's how we were getting different behavior on each call to that thing. Okay, so we're going to talk about some ways to do this differently in a minute. Now let's look at another example where nothing hidden underneath the covers here. I've got my AddOne function and calling it. Okay, so let's play our game one more time. And
wait, can you scroll down? I just want to make sure there's no funny business happening.
Yep, no funny business down there. No imports. Yeah. Okay. So I'm passing 4 to that AddOne. What's it going to return?
It should return 4 plus 1, which is 5.
Yep.
Although I was
already said. We try again. What's it going to return?
5.
Yay! It works. Okay.
All right.
So that's our example of referential transparency and pure functions. Tell us a little bit more about those, Josh.
Yeah, so the idea here is you want the ability as a programmer to look at a method call and be able to kind of mentally replace it with its value everywhere you see it. The exact same method call with the exact same value, because it really helps you understand what the heck is going on in your code, and it really avoids some of those magical kind of confusion moments of, oh my gosh, I didn't realize that I was bytecode rewriting some information for logging over here, and I threw an exception. And that totally crashed my program. But I don't know when I look at this method to look over there and see that. Or when I'm using global mutable state, I have no idea what the state of the global mutable state is when I look through the method So debugging just becomes that much harder. Referential transparency, as much as you can preserve it, can really make it easy as 4 + 1 in terms of debugging. What happens?
Yep. Yeah, and so pure functions like this AddOne function here, what they do is they will always map a given input to an output. So what that means is that every time I call this function, it's going to, if I call it with 4, it's going to produce the same output every single time for that given input. And so this makes it so we can understand our programs much more easily. We don't get into weird states where it's like, how did I get into this state? It's just, it makes it a lot easier to deal with our programs in this way. So this is an important concept in functional programming, and one that is in that cycle of learnings. It is one that is propagating much deeper into our object-oriented programming, and so that we can have programs that are easier to grok, easier to debug, easier to understand, and don't get into weird states that we don't understand how. So this is our first set of concepts: immutability, pure functions, and referential transparency. What else to add on that?
This is really the evolution of the prefer immutable objects from effective Java, which, when was that written?
2001.
Oh my God.
Almost 20 years ago. Yeah.
I don't want to think about that, but let's move on.
Let's move on to the next one. So
James, I was thinking we might start talking about the hardest problem in object-oriented programming, how to construct an object.
You'd think that would be easy, but let's go there.
All right. So here we start with a vehicle class that we want to build, and our vehicle class has a lot of parameters here, right? Like, I'm not a vehicle guy, so James, you might need to back me up on why some of these things are important.
Apparently, most vehicles have 4 wheels because that's our default.
That's our default, yeah. And vehicles can have less than 4 wheels or more than 4 wheels.
Amazing.
Man, yeah, okay. I mean, I haven't seen a vehicle in like years, or at least months. In any case, what's interesting here is we have different constructors to instantiate the vehicle with different, set of parameters. And each time we have to instantiate all these different fields. So we have, a vehicle can have a name, and then it uses the defaults. Or you can actually pass a value instead of a default, and then we can use these optional values. So like if you wanted to have a 6-cylinder vehicle instead of an 8-cylinder vehicle, or a no-cylinder electric vehicle, you can do that.
One of the great things in this example is that we are using immutability. So our static class vehicle is immutable, but that does mean we need to have all these different constructors to assemble the different possible ways to set those immutable values.
Yeah, and now we have a lot of duplicate code, and it takes a little bit more to maintain this. And every time we want to add a new optional parameter, we add a new entire constructor.
Yep. Yeah, so that's kind of the typical way that we do POJOs in Java, but you can see it's cumbersome. And so what did we do? What was the pattern that we developed to help us with this?
I believe it's called the builder pattern, which you're hovering over there. We can actually make another object that makes it easy to construct this object.
Yes, so let's go down to our vehicle builder. Here it is. So what's happening in our builder?
So the vehicle builder stores all of the possible state that you'd want to pass into the constructor effectively. It allows you to call methods to apply pieces of the state over time, including optional ones. And then it has a build method that finally calls a single constructor with all the parameters at once. So you end up with one single point of construction for the class, and the builder controls the flow through optional parameters and different ways to construct that class.
Yeah, and so like this has worked for a while, and it has helped improve us from where we were with just all the constructors. But I've had a lot of challenges with builders. For instance, builders usually aren't very good at conveying some of the semantics about what is actually needed by the underlying POJO data structure. For instance, if two fields are related, like I set one field and then I need to set another field, that's usually something that is not conveyed through a builder. And what can happen is you call build on the thing and then it throws an exception because you didn't do something right. So that's one of the challenges that I've had with builders in particular, is that it just usually doesn't convey the actual semantics of what the underlying thing needs. What other challenges do we have with builders?
You actually have to still maintain both sections of code. So you have to maintain the POJO and you have to maintain the builder. So if I make changes to the POJO, I have to make changes to the builder at the same time. So actually the cost of ownership is doubled.
That's true. And then also, with builders, things can get pretty crazy when we start having hierarchical things that we're building. So let's say we have our vehicles, but let's say now we have owners, and owners have vehicles. And now our syntax starts to get pretty gruesome here for how we will build a hierarchy of objects. So you can see just a lot of code here. We oftentimes get to the place where we have to be able to go from our immutable POJO back to a builder so that we can make modifications and then rebuild it. And so things get pretty nasty pretty quick with hierarchical objects.
This reminds me of trying to remove a member of a repeated field of a protocol buffer.
Fun, huh? Yeah.
Exciting times.
So what we are seeing with the kind of functional evolution of our object-oriented languages are some different paradigms for how we construct objects. And so in Scala, we have something called case classes, and in Java, these are the, what is it, coming in JDK 15 or something like this, is something similar to case classes, which are, I think, record types, and Kotlin has data classes, and so a lot of the object-oriented languages now are adding much easier ways, much better syntax for constructing objects. So Josh, walk us through what's going on here in this case class.
So primarily, I think I want to talk about there's a philosophical change in terms of how you design and craft your object, where there's a few components here I want to call out. One is the parameters can have default values and then not be specified. So you don't need a builder to be able to have default values anymore, because you can actually account for that in your constructor. The second thing is you can actually have named parameters when you construct. So you can provide, if we look here with this vehicle, you can use the name of the parameter, so you can provide only the optional ones, at the far right of your constructor. So that helps a bit. And the other thing is, all of the arguments to the constructor actually become members of the class. So you don't have to make getters and setters. If you look at case class owner there, it's quite simple. It's just I have a name, and age, and vehicles. Those are the pieces of data I need to know about. And those are the pieces of data I construct. And then the language builds in convenience mechanisms for you to build these effectively and to modify them effectively. If you look at that copy method, before we'd have to call .toBuilder and then modify the parameters that we want. In this case, the copy method is generated and gives us the same parameters as our constructor. So we can actually construct a new copy that has all the same data, but with a few things different.
Yep. Yeah, so this is, I think, definitely indicating that cycle where we made some pattern changes with builders, and now we're getting great language level support for constructing objects and making it much easier.
All right, so I think we're on to the next topic, which is, we've created these nice ways to construct objects and things, but what if I want to take a bunch of functions and put them together? What do I do, James?
Yeah, so combining objects we can do through a variety of ways, which we saw through case classes we're going to talk more about in a little bit. But what if we just have functionality that we want to combine together? we can actually use some of the things that we learned about in object creation to do this. So for instance, let's say I have a function and I'm still working with my vehicles, and my function is called balanced, and what it does is it basically just says, like, is this thing even? So that's assembling my function. So this is now a predicate of integer. And then we have another one called beefy. Like, is this thing, does it have a lot of cylinders? More than 8, then it's beefy. So we've got 2 predicates for integers, and we can apply those. So we have on our maybe number of cylinders, which is our option, we have a way to filter on that option with that function. We can filter on our option number of cylinders with our beefy function, and that's all great. But what we can do is we can actually take these 2 predicates and combine them together. And so the way that we do that is that predicate actually has functionality on it called a combinator, has a number of combinators. One of the combinators is OR. So because predicate has a function on it called OR that can combine with it another function, now we could take these 2 functions, combine them together into a new predicate, and then we can use that new predicate in our filter function like before. So that OR is just taking this is an immutable way to construct a new object, and that new object is both of those predicates combined with an OR.
Is this kind of like a builder from smaller components?
So I have had arguments about that with people, and I think it looks and feels a little bit like a builder, but you don't call that build on it. You're not doing this mutable state where you're mutating and then calling build. So I wouldn't really say that this is the builder pattern. I would say that this is just a better built-in way through combinators to create new combined things.
But you're still achieving the same goal of small classes with clear, coherent responsibilities, and then clear operations to join those together to make complex behavior.
And doing it all immutably. Yep. So one of the important evolutions that's happening in object-oriented programming is something called algebraic data types, ADTs. ADTs allow us a better way to represent data structures, and there's primarily 2 different ADTs that we can work with. There is a product type, and a product type allows us to combine together values. So for example, let's say that we want to combine together two values into a pair. Well, we can create a pair object to do that, or our language may have something like this built in. If we want to combine 3 different values together, we can combine them into a triple. There is language support in many languages for doing these without having to give them names, and these are called tuples. And so so this is just combining a bunch of values together.
It's kind of like those data objects we were looking at before, right?
That's right, exactly. And so this is called a product type. It's also called, you can call it an AND because it's ANDing together values, or you could also call it an intersection type. So different names for this. There's another one, which is an OR. So using those algebraic ideas of and OR into our type system and how we combine values together. So now onto the OR, we can do this. This represents something that is what's often called an either. So something that can either be an A or a B, for example. But we don't just have to deal with 2 values. We can have things that have let's say 3 values. Let's say it's a trither, and a trither can have an A, B, or C, and so we combine these together. And this is called a sum type, or you could call it an or a union. And so these data structures, this way of representing these types of values, can be really useful for being able to have our type system convey the semantics that are actually allowed. Oftentimes, what we would do in the past was maybe just leave one of our values as null and set another one. But that doesn't actually encode into our types the actual the actual legal values that are possible. And so with ADTs, we can much better encode them. So one of the ways to represent the or is with this either type. There is also there are languages that are adding direct support for some types into the languages with special syntax and making it easier to construct and deal with these sum types.
Most OO languages already have support for some sum types, right? Like, can't we just use inheritance?
We certainly can. So that's exactly what this example is doing, because I'm in Kotlin, and Kotlin does not have actual direct support for sum types. And so what I've done is I've done this through a sealed class. Then because I've made it sealed, you can't extend this anywhere else. So only right here can we actually extend this either type with our actual implementations left and right. And you'll see that left has a value left, right has a value right. And so both of those extend either. And then you can see the example for try there too, pretty similar. What is happened in a lot of modern languages that are using ADTs and supporting ADTs is pattern matching. Pattern matching that is able to look at the actual classes and be able to do smart things with it. So in this example, we're back to our sum type, our either, and you'll see I have, I'm using a left and a right sum type here, but now I'm gonna do my pattern matching. So I'm gonna say when R, and I'm just matching right now on that R one, when it is an either left, then I can do something with it. And Kotlin has some nice syntax here where it does the smart cast. It's like, okay, I know that R is an either.left, and so I'm only going to allow you to access that left property. I can't access the right property. Remember, left didn't even exist on right. So right has right and left has left. And so Kotlin, when we do that pattern match in our function that we're going to handle this with, it does that smart cast for us. But there's another nice thing with sum types and pattern matching is that if we don't handle all of the cases here, so if I comment out this one, then Kotlin gives us a compile warning and says, hey, you're not exhaustive. You are pattern matching on a sealed class, and it knows that in that sealed class, there are two things. There's a left and a right, and it's now warning us it's not exhaustive. I usually, when I'm writing Kotlin, or Scala has a similar feature, I actually turn this warning into an error. If you're not actually explicitly handling all the possible cases here in your pattern match, then it should be a compile error. So that's what I do. Okay, so pattern matching allows us to replace that visitor pattern with something that is much more concise and easier to deal with. What else to add on that? Yeah.
Aren't they discussing bringing that to Java after record types are out?
You are absolutely right. I don't know if that's JDK 16 or something else, but yes, so pattern matching in this way is, and not direct ADT support, but as we said, we can do the ADT part in other ways in languages today. Maybe at some point Java will get actual language support for ADTs, but they are adding the pattern matching, which will be really nice. So one of the great language features that we've seen started to be added to a lot of languages is extension functions. Extension functions are a kind of different way to do polymorphism, where we can add functionality to classes just by creating functions that add that functionality. So in Kotlin, the way that we do that is we create a function, iterable, and we can even use generic, so an iterable of char. We're going to add a new function available on that thing called sum. And so when we want to sum up chars for some reason, we can do that with this extension function. So now if we've got our list, which is an iterable of chars, we can call .sum on that, and that'll just work. And if we continue with this example, we'll see, all right, now we can add an iterable of string, and so that we can take strings as inputs in our iterable list and do that. But we've done this all with concrete types in that iterable of whatever. What if we wanted to make this generic? Well, what we can do is we can have an abstract class, toChar of t, and then have this invoke operation on it, which is going to return a char. And then we can do a string to char. So now we create a new function that is going to be able to take a string, turn it to a char, get the first one, and then char to char. So if we've got an iterable of char, but now we can do an extension method that is on our iterable of t. But it needs to actually take this toChar converter that knows how to take that t and convert it into something that then we can do our fold on. And so now we've got this new method sumT that we can call, where so now we can say list of chars, sumT, but then we need to give it our char to char. So that's great that we can do these extension methods with generics. But things start to get a little bit weird here because we're having to pass into sumT the actual converter that we need. So let's say we wanted to be able to do an iterable toChar. So we've got an iterable of t. Then we need to define that one, which we can do. It's a toChar of iterable t. But then that one needs to know how to convert the t to a char. And so now we need to start, let's say we've got a list of chars, and we want to be able to sumT those. Now we have to provide the whole chain of things that are needed to do all the conversions. We need to pass that all in explicitly. So the extension methods are great, but using them in this way to do these conversions requires us to be explicit about the ways that we're going to do those conversions, and we have to provide them. So let's look at Rust, which has a better way to handle this particular case.
Yeah, so effectively in Rust, it does what's called derivation, where it will attempt its best to kind of construct these generic types for you from the specific type that you have. So in Rust, we define our toChar as a trait, which is its equivalent of like a Java interface. It has a single function toChar that takes in the existing instance of a type and then returns a character or char. And so then we define implementations. So for a character, it just returns itself. For a string, we just grab the first character off and return that. And then there's this nice implementation where we can take in an abstract type and define it against any vector of any type and say, okay, if I want to define the implementation for a vector of any type, just give me the implementation for the type of the vector, the t, and then I will continue to kind of unwind these things, right? And so when we define sum, we just have to define one toChar interface for any possible vector of t that we have. And we can sum over this, and it will kind of infer through things what we need. So here, if you notice, we only provided toChar for generic vectors, for characters, and for strings. And so in this println, you see if we pass in a vector of characters in the first example, that compiles and works. If we pass in strings in the second example, that compiles and works. If we pass in a vector of strings, that will work because it will recursively look through the vectors and infer that, oh, the toChar for a vector of string or a vector of strings is the vector of strings passed in, and yay, it does all that magic for you. Same if we do a vector of cars. So why don't you can run this to show an example, and then I want to show you what failures look like.
So we can run this one and it'll work. But the important thing to highlight is that this is like the Kotlin extension methods that we saw, except for we don't have to do that explicit passing of the types that are needed like we did in Kotlin. So great, that one works. Let's go back to here and let's go change one of these cars to cars, chars. I'm just going to say differently every single time.
We know integers don't work, so let's call it an integer.
Yeah, so let's put an integer in there, and then let's try to run this compiler again. And what happened?
So you're getting two errors. One is it says that you can't make a vector of integers if you pass characters to one of the vectors.
That's right, and we can go fix that.
You're right. Thanks, Rust. But also, when it tries to find the trait toChar, it tells you it doesn't have one for integer. It doesn't tell you it doesn't have one for vector of integer because it knows it can follow vector of vector. And it just says, oh, I need one for integer. Go write one. That's it. It's wonderful. The compiler is doing all this work for us.
Yeah, and so this is a great evolution for OO, and the name commonly used for this is type classes, but I think Rust actually calls them something different from type classes. What does Rust call these?
I believe they're called traits and type traits. C++ calls them type traits.
Okay. So different names, but this idea of being able to, for the compiler to implicitly find what it needs to be able to fill in function arguments, essentially, because we've got our sum method, and it needs a tochar that can operate on that vector of t. So yeah, ad hoc polymorphism is also another term for this. Okay, so let's pull together a lot of these concepts that we've walked through into something that will make sense of why we need these things and how they can be useful. So in this example, we've got our vehicle. So you saw our vehicle earlier. It's our case class. It's immutable. It has those default parameters. We don't have any builders. Great. But let's say that we want to do JSON. We want to go from JSON to a vehicle. Well, and we want to have some validation built into this as well. So we're going to use combinators to build up some validators to validate our JSON. And so we're using something here called verifying. We're going to verify of string. We're going to get the first letter in that string, and we're going to verify that it is uppercase. And if it's not, we're going to return an error. And so this is using some functions. This or else is using a combinator to do our verification that a string starts with an uppercase letter. Then we're going to also do a different validator, which is we're going to validate that the minimum length is there, that the length is at least 2. And we're going to combine that using a combinator with our starts with upper function. So we're using combinators, and we are building up a validator. Now let's actually create a way to read our JSON object into a vehicle. So we're using, again, combinators. This and is a combinator that's going to take something that reads a property named name and uses the name validator on that thing. We're going to do a read int, but you'll see that for read int, I didn't actually tell it how to read an int. So this is where we actually see those type classes, that ad hoc polymorphism come in, is that read actually takes a reads of t, so it's parameterized like we saw before. This is in Scala, but you saw something very similar in Rust, where there is something that knows how to read an int and handle that. We can also read a nullable int, which is going to be an option, which is our ADT, our sum type, for something that can have a value or not. And so we're seeing a lot of these concepts that we saw, ADTs, combinators, type classes, all coming together so that we can create something that knows how to read JSON, knows how to validate that JSON, and turn that into our case class of a vehicle. Okay, that was a lot of stuff there. Josh, what do you want to clarify?
So then I think the most important thing is if you look at this JSON that we take in, if we take in name and num wheels, we're not taking in cylinders. We can actually parse that JSON, run our validation logic, get our errors out. And here you notice that the response is a ADT itself that we can pattern match on and say, if we're in the error state, we do some errors. If we're in the success state, we print a value. And you can really start to see these things come together. This notion of composing small bits of logic that are easy to test, easy to reason through, making sure that my combinations of that logic is easy to understand and reason through, and then build a very complex program from simpler components. And that's really the focus of what we're going after here with functional programming. That's really where we see huge benefits for Java developers. Small, simple components composed together.
And we haven't even talked about the benefits of testability of this stuff, but that's certainly a huge benefit of all of this, is being able to test these small pieces independently and validate that they are correct. So yeah, so that is our example that brings it all together and shows you how you can use immutability, how you can use case classes, ADTs, how you can use ad hoc polymorphism, and for a serialization example, which is just one way that this all comes together well. There are many others to explore as well. All right, so hopefully that was useful for you to see how our programming is changing and evolving, and how our object-oriented programming is in some ways becoming more functional to allow us to more easily test, more easily understand our code, all that kind of stuff. So if you want to find the source code that we've been walking through, that is all up on my GitHub, github.com, James Ward, and then OOP-evolution. All right, what else, Josh?
Just want to thank everyone for listening, and encourage you to take a look at some of these languages coming down the pike and seeing what's coming in Java, because it'll make it there. It'll make it there.
That's right. Evolution happens. Thanks for watching.